In today's video, we primarily want to address what a star's color can tell us about the star, about stellar populations, and lots of other things, as you'll soon see. So, you can remember from the Light and Matter unit, in fact a lab that we did in the Light and Matter unit, that you can directly determine a star's temperature because of its color. Its color is not because of its chemical composition for the most part. I mean, every once in a while you'll get various slight hues in the star's atmosphere that have something to do with chemicals, but that's relatively rare. Generally speaking, a star's color is directly determined by its temperature. So if you can map the intensity of a star's light as a function of wavelength on a plot, then the peak of that tells you its temperature. That's Wien's displacement law, if you'll remember. So red stars are the coolest stars in temperature. For example, Betelgeuse and Antares. These are red-colored stars, and they have temperatures of around 3,500 kelvins. Whereas other stars, for example, the stars in Orion's belt and stars in the 30 Doradus cluster, they have much higher temperatures, and they tend to be kind of bluish in color. Our Sun itself is kind of average in that extent. It's a yellow star, its surface temperature is around 5,800 kelvins, and it's pretty much right in the middle of that temperature spectrum, so to speak. So here's a picture of the constellation Orion showing the famous stars in there. We have Betelgeuse, the bright red star, cool in temperature, 3,500 kelvins. And then you have the bluer stars, Bellatrix, Rigel, Saiph, Mintaka, Alnilam, Alnitak, Cygnus Orionis, and the star Maesa, or sometimes called Hecate, making up the head of Orion. And the Orion Nebula here is lit up like a firecracker by 4 very bright stars, the Trapezium cluster, all of which are also kind of blue in color. And every single star, as I've mentioned in the last discussion, whose name I just pointed out, is going to explode. Here is a picture of the 30 Doradus cluster, one of my favorite astronomy pictures of all time, again taken by Bob O'Connell and colleagues at University of Virginia and elsewhere. And in the middle of this is the brightest, most massive star that we know of. It's R136A1, has a temperature of about 53,000 kelvins. Its mass is about 265 times the mass of our Sun. Using our current understanding of what's going to happen to such a star, we think that eventually what's going to happen is photodisintegration, that is, the energy of photons, gamma rays in the core of the star will eventually cause the core to become unstable and bust apart the heavy nuclei that have formed there, and that will cause the star to lose its supporting power, and the core will end up collapsing into a rather large black hole. And there might not even be much of a supernova explosion from that. That's kind of different from the previous ideas that we had about such stars, but this is a picture that's been refined over the past decade, or continue to be refined, and the idea of what we think will happen has changed over the past decade. But there are a lot of stars in this cluster that will definitely explode as supernovae. In fact, probably most of the big bright ones that you see in here are going to have that fate. We have a number of stars here that have many dozens of solar masses, and it's just a really spectacular region. So here is a picture that we showed before back in the Light and Matter unit, the black body curves of objects of different temperatures. And again, just a reminder, as the temperature increases, the peak wavelength decreases, because remember, peak wavelengths have more energy, and therefore once the temperature increases, it becomes more efficient for the object to radiate at shorter wavelengths. So people sometimes wonder, well, why doesn't R136A1 look purple or ultraviolet-like? Well, long story short, it's because we don't have eyes that are very sensitive to ultraviolet light. And as such, what's happening with R136A1 is it's really just off the charts pretty much in all parts of the spectrum that we can see, and it peaks well into the ultraviolet part of the spectrum, but it still radiates a whole lot throughout the visible part of the spectrum. So even though it radiates more at purple wavelengths than it does at red wavelengths, it still radiates a whole lot at red wavelengths. So just averaging all of those together, so to speak, well, technically doing a weighted average, that makes it appear bluish to our eyes, just like the stars in Orion's belt. These stars all have temperatures of between about 25,000 and 40,000 kelvins, so they radiate the great majority of their energy in the ultraviolet spectrum as well. So here is a spectrum of a star. I'll give you 2 seconds to guess which star this spectrum represents. This is the spectrum of our Sun. This shows lots of dark spectral lines. As we mentioned in a previous unit, these are due to various absorption features which occur when an atom or molecule in a relatively low energy state is able to absorb photons or ranges of photons that correspond to energy differences between different energy levels in the atom or molecule. And you have lots of these with our Sun due to a large variety of elements and low energy compounds in our Sun's atmosphere. And this shows the spectra of various types of stars. We talked about the OBAFGKM classification scheme. We're going to review that again today. But originally that was devised to denote different spectral features in the spectra of different types of stars. And notice that with the M stars, the cooler stars, you're dealing with a lot of spectral features due to molecules in the atmospheres. When you're talking about low temperatures, you don't have enough energy to bust apart those molecules, so the molecules can remain intact to a large extent in these stellar atmospheres of low temperature. So again, we've discussed how these form before, so some of this we're going to go through kind of quickly, but if you need to pause at any point and take in some more of these details, then just pause the video and read through some of these slides. So again, we've gone through the OBAFGKM scheme before, and the mnemonic that's often used for that again is "Oh, be a fine girl," or "Guy, kiss me." Now, we have two new classes, as we've mentioned in the extrasolar planets unit, the classes L and T, representing these brown dwarf objects that we're going to discuss later on in a future discussion of this PowerPoint. So there are also numerical subclasses for each of these classifications. For example, the hottest B star is a B0, whereas B9 is the coolest B star, and then the next coolest star after that would be an A0 star, and then you go up to A9, and then F0 all the way up to F9, and then G0 all the way up to G9, etc. Our Sun is a G2 star. That's something that I would like you to remember, that our Sun is a G2 star. So here's a little chart showing how these classifications correspond to temperature. And again, I should mention that any main sequence O star is going to explode as a supernova, and probably most main sequence B stars are going to do that as well, or at least a fairly decent percentage of them are going to explode as supernovae. And then there's our Sun in that range, our Sun being a G2 star, so it's closer to 6,000 kelvins than 5,000 kelvins, and as you get cooler, you end up going down the scheme. So here we are again, and here you can see the actual plots of intensity versus wavelength of different spectral types. You'll also notice some Roman numerals on a lot of these things. The Roman numerals denote the actual type of star it is. In other words, what's the difference between a white dwarf star that's an O star and a blue supergiant star that's an O star. So the way this works is if you have a star that's a main sequence star, remember about 90% of stars are main sequence stars, we denote the Roman numeral 5 after this number. And then if it's kind of between main sequence and getting into the red giant phase, or the whatever giant phase applies to that star, then it would have a Roman numeral 4. And then if it's actually in the red giant branch, what exactly that means we're going to talk about soon, then we give it a Roman numeral 3. If it's a supergiant star, like a blue supergiant or a red supergiant, we give it a Roman numeral 1. And if it's between a giant and a supergiant, we give it a Roman numeral 2. So that's what those mean as well, and that's something else that I would like you to know. Here they are again. Now, what is the red giant branch? What is the main sequence? What is the white dwarf region? Well, in order to help us to better classify stars after these OB-AFGKM schemes had already been developed. Henry Norris Russell and Einar Hertzsprung came up with a very nice way of doing this, and that is now known as the Hertzsprung-Russell diagram. By the way, they devised this method independently. So again, this takes us from OB-AFGKM, from the hottest to the coolest, and the temperature is plotted on the horizontal axis, but it is plotted in such a way that temperature increases going from right to left, so that if you read it going from left to right, you would read OB-AFGKM, which again is "Oh, be a fine girl or guy, kiss me" for the mnemonic. And again, L and T have crept into this as well, so my little mnemonic for that would be "Oh, be a fine girl or guy, kiss me, little troll," which I've mentioned is a great pickup line, so definitely consider using that sometime if you're in the mood to get slapped. So again, O stars, these things, at least on the so-called main sequence, again, we're going to get to that soon, although we've discussed it a little bit before. It's stars that are doing what our sun's doing, fusing hydrogen into helium in the core. But O stars that are on the main sequence, they're only going to live for typically like a few million years or so on the main sequence, and then they're eventually going to expand, and in some cases not even expand before they explode into smithereens. So again, our sun is a type G star. The coolest of the main sequence stars are the red dwarf stars. These are the type M stars. So here is an example of one of these Hertzsprung-Russell diagrams. It's a plot of luminosity versus temperature. Technically, it's a plot of magnitude versus temperature, because what we actually observe is a star's magnitude, but that can then be converted into a luminosity using a formula. So using this scheme, we see our red dwarf stars down here in the lower right, and then we have our blue giant stars up here, and then blue supergiants over here, and then red supergiants up here in the upper right part of the HR diagrams, it's often called, because a lot of times people get tired of saying Hertzsprung-Russell. And then we have these special stars, stars that are very hot, but also not very luminous. We realize that these things are very tiny in size, in a lot of cases similar in size to, or sometimes smaller than, Earth. But what they are, well, we're going to discuss that later on. Not today, though. But you also have red giant stars in here as well. For example, the star Aldebaran. Aldebaran, which we've had on our constellation quizzes, is pretty much an example of what our sun is going to be like in, say, about 5.5 billion years, as is the star Arcturus in Boötes. So these are in what we call the red giant branch. This is a branch that has left the main sequence, and we're going to talk about exactly what's going on there in a future discussion. But notice something else on the main sequence. So 90% of stars are on the main sequence, and spoiler alert now, the reason for that is because stars typically spend about 90% of their lives fusing hydrogen into helium in their cores. But as you go from lower right to upper left, you are increasing in mass and decreasing in main sequence lifetime. So our sun being around here, its total lifetime from birth to going onto the red giant branch is going to be about 10 billion years. And then as you get up toward over here, well, Sirius is going to have a total lifetime of less than 1 billion years. Sirius is a bit more massive than our sun. So, and then Vega is even more massive, and then you start getting up toward these stars that are going to explode. So what we realize now is that any star that begins its life with more than about 8 times the mass of our sun is going to explode. Bellatrix is an example of that. Spike is an example of that. And here you have Betelgeuse, which had started its life somewhere around here and is now in the red supergiant branch. Same with Antares and a lot of these other stars as well. Polaris is kind of borderline in terms of whether it's going to explode. I think it started its life with about 7 or 8 times the mass of our sun. So exactly what's going to happen with Polaris depends on the amount of heavy elements that it has, but it's somewhat borderline. Now, again, I already discussed how this was developed, and we already also talked about these luminosity classes, telling the difference between supergiant, between giant and supergiant, and giant branch, and subgiant, and main sequence, going from 1 to 5 on the scale. And by the way, white dwarf stars are sometimes simply categorized as D if it's a white dwarf star, because a white dwarf doesn't actually fit into any of these, technically speaking. So they're often categorized as D, or sometimes with a Roman numeral of 7. So again, here's another HR diagram showing a few representative stars. And another one. This is the type of plot that somebody might make of a large cluster of stars, and that's something that we're going to get to later. But making a plot like this for a large cluster of stars allows you to figure out the age of the cluster quite precisely, because something we've discussed before, all stars in a cluster form at about the same time. Yeah, the more massive ones form first, but they end up going supernova anyway. But the less massive ones, the ones that are going to live for billions of years, they form pretty much at the same time. Here is a very detailed HR diagram. They probably can't see the details of this in the actual video, but our sun being right here, and then you get into the giants and the supergiants up here, and then some examples of white dwarf stars. The well-known stars Sirius and Procyon, by the way, both have white dwarf companions. So here's a slight zoom in on that. And here's an example of another HR diagram that's actually plotted simply as magnitude versus color. And again, 90% of stars are on the main sequence. Now here are some examples of temperatures and luminosities, and that star R136A1, again, its surface temperature is around 53,000 kelvins. I think that's an O3 star, but that is the brightest, most massive star known. So, absorption lines give us more insight into what's going on with a star. We've discussed before that based on stellar absorption lines, you can, and the widths of them and how those widths behave, we can determine such things as the rotation rate of a star. And even if we didn't have a black body temperature for a star, we would be able to discern something about the temperature of the star based on the width of those absorption lines, because after all, a higher temperature star is going to be dealing with faster moving molecules, and therefore you're going to have a larger width due to the Doppler effect. So again, we discussed a lot of this back in Unit 3, so if you need to check out any of this in more detail, then you should pause the video. So again, just exploring some of these spectral line types of features. And again, once you start to get toward cooler stars, the K and the M stars, you're dealing with molecular lines. In fact, often molecular bands. You'll have entire bands of absorption features in the spectrum. That's what makes water vapor and, to a lesser extent, CO2 such powerful infrared absorbers in our atmosphere. The fact that they have these large bands of wavelengths in which they absorb all of the, or at least a large percentage of the sunlight that, or I shouldn't say sunlight, but radiated light that's in those wavelength bands. And then apparently some of the apparently brightest stars, ones that you all know about quite well, either from the constellation quiz or because of the fact that they've been mentioned numerous times in class. And again, for example, Sirius, it is a main sequence star, but on the other hand, Canopus, which it's not visible from our latitude, but we being in Northern Virginia, it's a supergiant star. And Capella is a giant star. And remember that Arcturus is a red giant star as well, so there's that Roman numeral 3 afterward. Now, something that might have occurred to you in the last discussion. We talked about how we can determine distances to stars, especially stellar standard candles. For example, there are a lot of stars in our galaxy now for which we can make direct distance determinations just based on geometry. So it doesn't matter how bright the star is, as long as unless it's too bright. For example, we still have uncertainties on things like the brightness or the exact distance to, say, Betelgeuse, because Betelgeuse is so bright that it immediately saturates the detectors of the Gaia spacecraft, so it can't really look at Betelgeuse. But the dimmer stars, yeah, we know those distances because just direct geometry. But what about those standard candles? Let's say you're looking at a star in some other galaxy, some Cepheid variable, and you think you know how bright that star is based on the period luminosity relationship, and based on how bright it appears in the telescope and how bright you know it is, you use that formula brightness equals luminosity over 4 pi distance squared to determine the distance to that star and thus to our galaxy. So something that might have occurred to you during that time was, well, what if we have a star that looks very dim, not because of the fact that that galaxy is really, really far away, but maybe it's because of the existence of a lot of dust along the line of sight between us and that galaxy. If there's a whole lot of dust, then what might actually be the case is the galaxy could be a lot closer to us than we think. And that itself could have potential implications for trying to figure out the age of the universe. If we have distances being farther than we think, then that would mean that the universe is older than we think. But if the distances are actually closer than we think, then that would mean that the universe is a little bit younger than we think. That's something that we'll come back to when we talk about cosmology. So how do astronomers figure out whether a star is dim because it's really far away from us, or whether it's dim because the light is being absorbed by dust between us and the star? Well, there's a very good way. Consider this picture. You've seen this picture before. It's the famous Pillars of Creation in the 16th object in Charles Messier's catalog of fuzzy things that aren't comets. And notice, look through here. Ah, look at this. We see stars here. But those stars look a bit redder in color than, say, some of these other stars. Now, these are not actual colors. This is using the Hubble color palette. This is actually more of an infrared image than a visible light image. But there's still that effect here, the fact that you can see these stars, but they look a bit redder in color when viewed through this dust. Well, that's exactly what dust does. When you have these dusty regions, which are what some of these what all of these various dark nebulae are in the sky that sometimes you can see with binoculars or a telescope, in these dusty regions, well, the dust typically has grain sizes on the order of about a micrometer. Well, a micrometer is longer than the wavelength of visible light, but not so much longer that it's not going to allow some visible light to go through. Well, what type of visible light is going to go through? Well, the longer wavelength is going to go through, because remember, that's the idea about wavelength. Wavelength gives you an idea of where the photon could actually be. And if the wavelength is on the order of or longer than the size of the dust particle, well, it's essentially like the thing that's traveling through, the light particle, is potentially going to ignore that dust particle. It's as if it's not even there. Again, that's how you are able to receive radio stations inside, even though you have walls. Well, the wavelength of the radio stations is longer, typically, than the thickness of the walls of your home. Well, in fact, you can see a lot of this if you're in the country and you're able to see the Milky Way itself. You'll see that it has dark bands through it. That's dust. Well, here's the thing. We have space telescopes and other telescopes that are sensitive to light in the infrared. So if there is dust there, we're going to be able to see through that dust in the infrared part of the spectrum, but not in the visible part of the spectrum. In fact, recently the Spitzer Space Telescope, which gave us a very nice insight to the infrared universe, Spitzer has been shut down as of the end of January of 2020, but we're still, of course, going through all of those data from the Spitzer Space Telescope. But the point here being is that the dust grains are blocking the short wavelength light, the light that's a wavelength noticeably smaller than the size of the dust grain, but it's allowing the longer wavelength to pass through. So it's either blocking or absorbing or scattering the short wavelength light, but the longer red light is allowed to pass through. So here's a nice picture of one of my favorite dark nebulae, Barnard 68. Barnard was an astronomer in the late 19th century who made a big catalog of a lot of dusty objects, dark nebulae in the Milky Way. I don't think he realized that they were dust yet at the time. But, oh, and by the way, Barnard is also the person who is the last person ever to discover a moon around a planet in our solar system by direct visual observation from looking through a telescope. He discovered Jupiter's moon Amalthea in, I think, around 1892 or something like that. But after that, everything else was discovered based on photographic plates or CCD images. But anyway, this dark nebula around here, notice that in the middle of it, it's, well, dark. But around the edges, you can start to see stars, but they're fairly dim, and they look kind of red in color. Indeed, when you look at the same object through infrared wavelengths, you're able to see a lot of these stars right behind it, because the infrared light is able to pass through because it is significantly longer in wavelength than the sizes of these dust particles. Now, because of this reddening, what happens is the short wavelengths of the stars are absorbed, but they are re-radiated at longer wavelengths because the dust itself absorbs these and it scatters a lot of them, but it also ends up heating up and re-radiating at infrared light. So in terms of absorption, this is kind of the inverse of a black body spectrum. You have a peak absorption at short wavelengths, and then you don't have so much absorption at longer wavelengths. Well, taking that extinction, as it's called, into account, astronomers can correct the distance formula for comparing stars, for comparing absolute versus apparent magnitudes. So again, if you need to pause at any point, then just pause the video, but a lot of the stuff we've been through in an early unit. So dusty stuff tends to have some more in the way of heavier elements in it to some extent, and that tends to come after a number of generations of stars have gone through their lives. Here's a picture of the Eagle Nebula as a whole. This is a true color image, and again, the pinkish glow is from hydrogen emission. And this right here is that big pillar that you saw in the Pillars of Creation, but notice that in visible light, it's harder to see it because of the combination of dust and the hydrogen emission from this region. So zooming in there, here's kind of the box that's used for the famous Pillars of Creation picture. So zooming in there with visible light, and then the actual famous Pillars of Creation image from the Hubble Space Telescope of M16, the Eagle Nebula. So hopefully this was illuminating in terms of the effects of dust on stars and how astronomers can measure those and correct for those. And it is something that can just be plugged into a formula after it's being measured so that we can get a corrected distance to, say, a star in a distant galaxy. And also how a star's color affects its temperature and what we can learn about the star. We'll go into a lot of these details in more time as we introduce additional concepts. For example, how stars form. That will be in a discussion soon to come. And after we've discussed that, then we can merge that back with our discussion of the Hertzsprung-Russell diagram and how astronomers can use that to determine the age of a cluster. So next time we're going to talk about how massive stars get and how we determine these masses and the various types of stars out there in terms of the range of their masses. So if you have any questions, please let me know, and hope to see you then. Thank you.